Okay. Last time we already talking about multi-vibrator. Basically, they get three. One, two, three. First one, they call a bistable. Bistable, that's just using the flip-flop. And a flip-flop, they get the output either high or low. And the second one, they call a stable, free running oscillator. That means they generate the clock coming out. Okay. And number three will be monostable. That also known as the one shot provide single output points. Okay, and you can specify the time length when it's triggered from an external source. And the capacitor jack and the discharge delta VC equal E1 time 1 minus E power minus T over RC.
Can
Okay,
you just one time explain the one shot one more time? The one shot.
the one shot that the mono stable. That means every time trigger they given you only one point coming out. That's why they call it one shot.
Okay.
And you see the difference with the art stable. Art stable, when you turn on the power, automatically clock coming out. One follow the other. Okay.
Okay.
And all of the formula for delta VC in here, we already explained to you. Okay. And now this time I try to move it, uh, make it more clear so we can get more room in order to explain for you guys. Okay. So basically, you can say if you on the connect to the number one, okay, then you get a current flowing, and they will be charging up the voltage on the capacitor. The maximum voltage charging on the capacitor will be 5 volt, right? If you keep at the position 1 for long, and the battery capacitor charging maximum up will be 5 volt, cannot be more. Okay. And also they given you the formula. How do we calculate the time for the capacitor charging or discharging? So now go back to capacitor in the circuitry initially discharge. That means 0 volt. And they want to know voltage on capacitor 0.5 millisecond after the switch is moved from position 2 to 1. And the answer will be 3.27. That's what we did last time. So you get any question in this problem? You can calculate delta VC equal E. Okay. Time 1 minus E power minus T over RC. So on this problem here, okay, you need to know what is E. Okay. E means the difference between the initial voltage on the capacitor and the voltage capacitor try to reach a 5 volt initial 0. So that's why you get 5 volt. Okay. And the time t equal 0.5 millisecond. Okay. So that easy to calculate the delta VC. Okay. Any question? If it's not, go to a second example.
Let me go
Okay.
back. Oh,
Yeah. You get any question?
Can you go back?
Go back. Get it?
Yes. Thank you.
Okay, now a second one, they still moving here. Okay, however, they will be asking for time. How long? Okay, after switch is moved from position 2 to 1 to reach 3 volt. So basically you're using this formula. You need to know E. Okay, and also you need to know delta VC. E will be the difference between the initial voltage. They did that 0. And now they want to reach 3 volt, right? Okay, A will be the difference between initial voltage 0 and the voltage try to reach. That means if you keep at the position 1 for long, they will be reach 5 volt. So they will be 5. And now delta VC, that means what the voltage capacitor will be charging up. So they initial 0. They want to charge up to 3 volt. So that's why you can get 3 volt.
Hey, Mr. Pham, that's a little bit confusing because on the third line, it says to position 1, will it take to the capacitor reach 3 volts?
That means capacitor will be charged up to 3 volt. Correct?
Correct.
Okay, so that's why delta VC initial 0, but they charge to 3 volt. So that is the voltage charging on the capacitor.
I thought the E was 3 minus 0 then. See, because you always...
Yeah, that's what I said. You can get 3 minus 0. Okay? But the thing is, okay, if you want to make it a little clear, then you can say 3. Is it okay?
Okay. So that's how you got the delta VC?
Yeah.
Okay.
That means the voltage charging on the capacitor.
So, Mr. Pham, you are not using a formula 1 to find out delta VC, am I right?
That 3 volts is just the capital E in the formula for delta VC. That's just the first step of the formula.
No, my question is in earlier example number 1, we use delta VC formula. Delta VC is equal to E into bracket 1 minus E to the power of negative T over RC. Because in that case, time was given, but here we don't use the same formula here to find out delta VC.
The thing on the other one, they asking for the voltage charging on the capacitor. On the second one, they asking for the time. For the capacitor, take how long? They charge up to 3 volt.
Okay, got it.
That are two different.
The formula is actually the same, except you're rearranging it. So that's you're looking for delta V or T, but it's actually the same formula.
That's a different formula. If you're looking delta VC, that's a formula different from the calculated time. You see, you get two formula.
Yeah, where I was mixed
See,
up.
you get this one. This one is using to calculate the voltage charging discharging on the capacitor. However, the second one here, this is a formula to calculate the time. How long they can be charging or discharging. That's a quite different formula. Then depending on what the question they want to asking you. On the number 2, they asking you how long. That means they asking you for the time.
But so, okay, am I incorrect in saying that to be able to complete the formula for time, you have to first do the formula for delta VC because that's part of the formula for time?
Right.
And the 3 volts and the 5 volts represent the capital E in both of those respective formulas.
You mean the capital E nothing to do with 3 volt? What's the definition for the E? That is the different voltage between initial voltage
Oh, yes. Okay, I see my mistake now. Thank you.
and voltage try to reach, not the voltage they already get there.
Right. Okay, thank you. Thank you. So it's
Mr. Pham,
3 divided by 5.
Yes, sir.
Mr. Pham, what I see this, both the formulas are same, but the rearrangement is different. In one case, we find out delta C, in another case, we find out time T. So if anyone remember one formula, and if he's good at maths, he can find out another formula. He can use it to find out another thing. Am I right?
Yeah, but you don't have to. This one, basically, they will be delta VC, okay? I try to correct, but still missing.
Oh, so that is delta VC.
Right.
Yeah, that's why I was a little bit confused. So what is delta V and delta VC? Okay, thank you so much. I appreciate it.
Yeah, Mr. Pham, go ahead, finish what you're doing, then I'll ask.
Yeah, the thing I try to correct it today, but still missing. Okay.
Okay, but where I was getting confused is there's 2 words that you've been using a lot. The initial, which is where the capacitor is at initially, and then what it's trying to reach. So when you said from position 2 to position 1, it'll take the capacitor to reach 3 volts. I thought we were trying to reach 5 volts.
Now that's quite different. Okay, E mean what? That means the difference between the initial will be 0, right?
Okay. Initial what? Initial what?
The initial, that means discharging.
The initial voltage.
So the initial, which is 3 voltage.
No. Capacitor initially discharge.
So 0 volts.
0 volt.
Oh, okay.
Okay, now what that means?
Mr. Pham.
Wait. Try
Mr.
to
Pham.
reach. What that mean? That means if you connect this thing forever, what the voltage on the capacitor?
5.
5 volts.
They must be 5 volts that they can reach. Try to reach.
Okay.
However, 3 volts in here. That means they only go up to 3 volts, not try to reach. Okay?
Okay, so that where you got reach there, it's kind of like a word thing, because you've been using different words, and I've been trying to correlate that with what you're doing. Okay, so all right, so it's initially at 0 volts, but it's trying to get up to 5 volts, and that's E, so it's 5 minus 0. And then the delta VC is after so much time, you want to go from 0 to 3 volts.
Yeah, they've specified they want to know how long it takes for the capacitor to reach 3 volts on its way to 5 volts.
Okay, yeah, that sounds a little bit better.
You have to basically, you have to understand that a basic definition. Okay, now, so the capacitor initial charge to 1 volt. Okay.
So here E will be 5 minus 1, am I right?
Yeah, you're right. Okay, so no matter what calculation, you need to know E.
Okay. 'Cause
5,
it's trying to get the 5, but initially it starts at 1.
And so delta VC will be 2 volts because we're going from 1 volt to 3 volts.
yeah, that's a really easy one. Three volt. Okay,
Okay. Yes,
now make it a little more clear for your line, okay? So if you're doing correctly, you can get 0.326 millisecond. Okay, number 4. Initial charge to 4.2.
4.
Okay, so initial charge to 4.2.
and it wants to get the 5, so it would be 5 minus 4.2.
I don't know yet.
That's E.
I don't know
That's
yet.
E.
That's E
Depend.
though.
Depend. Okay, I only thing is make sure you understand initial charging on the capacitor already 4.2.
Right. So
Now
what?
they move this way.
Okay.
Okay, the capacitor will be a source, and they will be discharged through the resistor. Okay, so question A, what the voltage capacitor try to reach?
0.
0.
0.
Exactly, I said to turn on your car headlight. Forget to turn it off next day. I guarantee your battery will be 0. That they try to reach. So you understand E equal to 4.2 minus 0. Okay?
Hey, Mr. Pham, it's not 0. It's not 0 minus 4.2.
We not get a negative number. Have to
Okay.
be positive. That's
Okay.
just telling you the difference.
Okay.
And they want the time for the capacitor to drop to 1.5 volt. So now that will be telling you delta VC equal.
So it's 4.2 minus 1.5.
Exactly. 4.2. 1.5. Okay? That means you can substitute into the formula and do your calculation. So that will be a 0.484 millisecond.
Why do we need to know how long it takes to charge, or where do we use the time?
Okay, the question is, if I want to know, okay, at the beginning they get 4.2 volt. I want to know how long it takes so they can drop to 1.5 volt.
That's 2.7, Mr. Pham. Delta VC is 2.7.
Okay, if you do it, what you get? 2.7.
2.7.
Okay, so now you already know how the capacitor charge or discharging. Okay, you can calculate more accurate. Then normally they're talking about time constant. That means T equal R times C. That is the time for capacitor to reach 63.2% of the maximum value. This is more detailed to do the calculation. Okay, R stable. That's what they call a free running oscillator. Okay, you can go into the electronic store to buy an oscillator. However, they will be asking you what frequency. You can say 10 kilohertz, 100 kilohertz, or whatever. When you connect the power to that oscillator, automatically they coming out with the square wave. That means only in low and high, 0 and 5 volt. And with the frequency, you bought it. And now that's what they call a free running oscillator. Okay? But in this one, they can build from the Smith trigger 74HC14. That's just the IC. Look like inverter. You see that? 74HC14 high speed CMOS. Okay? And they just an inverter. If you get a 0 in, you get a 1 out. You get a 1 in, you get 0 out. Only the difference is what? That means the voltage input and the voltage output. Okay?
Mr. Pham, do you have to specially handle the 74HC114?
I think we have.
I guess what I'm asking, you can't handle it with your fingers, is that correct?
Yeah. No big deal.
Oh, because some ICs, you're not allowed to touch them with your hand because of the moisture.
Now that normally at work. Okay? At work, you know, the board with the CMOS, you have to be careful. However, on the single IC in the lab, that to me is not a big deal.
Okay.
Okay? That not mean every time you have to connect your hand to the route. Okay? That is too many things. We don't want that. Okay. Now, what in
What about
here?
with a rubber glove?
Yeah. In here,
I'm asking you, are you allowed to handle them with rubber gloves?
I don't know yet. Normally, you're working on the lab. I mean, on the band. Okay, they get a rip wrap connector to the route. Okay, and if you say you're using the rubber, you know,
Gloves.
yeah, then I think that maybe can handle that. But normally to me, I don't care.
All right, thank you.
Okay, now if you get a 0 in here, output will be 5 volt. Okay, I'm talking about logic fault. And that will be what? 5 volt. And that will be get the current flowing and charge on the capacitor. And when the capacitor keep charging up to be a logic 1 input, then the output will be 0. Okay? So basically you can see the output look like this one here. Okay? 0, 1, 0, 1. and will be run forever. That will be free running. And now we go into the detail. How do we do the calculation? Okay, what they say here, when VC reach positive going threshold, VT plus. Now, how much you understand when they say VT plus?
That's the point where the input turns to a logic 1.
Exactly. That means VT plus, that means stack logic 1. Input. And you understand for TTL logic. Logic 1 will be 2 volt up to 5.5 volt. Logic 0 will be 0 to 0.8 volt. But this is special IC. Okay? Only thing is the input get up to VT plus, then they be considered to be logical 1.
So
Okay?
anything 2 volts or higher.
Yeah. And also you can get another one VT minor. They will be stack up the logical low. Okay? That's how. Let's see. Now we see here. Okay, now they given to you this circuitry here. Okay, I and C. They want to get the label for waveform of the Smith RC oscillator. And they given the following specification for Smith inverter. VCC 5 volt, V out high 5 volt, V out low 0 volt, VT plus 2.75 and VT minus 1.67. Okay, now what happened when you just turn on, okay, the power, then this will be 0. Capacitor shorted to the route. Okay, so that's why 0. Output logic 1, they will be 5 volt. And then they will be charging on the capacitor. You can see here. Okay, at the beginning, output will be logic 1. Okay, now capacitor will be charging. Okay, so when they charging up to what voltage? 2.75, right? You see that? They will be keep charging up to the 2.75 volt. When you get a 2.75 volt here, so the input now at the logic 1. Output will be a logic 0. So that's why they will be output, they will be go to 0 right here. Okay? And the capacitor now they will be discharged. Okay? When they discharge to what voltage here?
1.67.
1.67.
And again, the capacitor never fully charges nor fully discharges.
Yeah,
It just goes between those two values.
1.67. Okay, then turn it out, output high again, and they keep going. Okay,
And Mr. Pham, if I could jump in. So as Adam was saying, since it goes between those two values, basically this device is charge, discharge, charge, discharge, charge, discharge. So it's just keep going 1 0 1 0 1 0. Is that correct?
yeah, that's what you can see the output. 1 0 1 0 1 0. Run forever.
Right.
Okay, now you can changing the frequency. Okay, or by changing the value for I and C. So what they want to do here, they want to calculate the time high, T high, the T low. That means how long they high or how long they will be low. Then also duty cycle and the frequency. If they given you R equal 10K and C equal 0.022 microfarad.
And Mr. Pham, just as a question, so up those letters where it says UTP and LTP, is that upper threshold point and lower threshold point?
Yeah,
Okay, thank you.
that voltage threshold upper, okay, and voltage threshold lower. So now if you want to calculate the time, the formula will be T equal, what T equal? Is it RC, right?
RC natural log
Okay, RC ln
times 1 over 1 minus VC divided by E.
RC
Ln natural log.
1 over, right?
Yes.
1 minus delta VC
Over E.
over E. So
The whole thing.
in order to calculate the time here, then you need to know delta VC and E. Okay? Now, if I want to calculate the T low, that means here. Now here, T low, right? From here to here. Okay? Time low. RC you already know. Only thing what you need to do is you need to know what the delta VC and what E. Okay? So we need to know, okay, delta VC for the time low. That means here. What delta VC equal? 2 point minus, correct? That means the voltage they will be discharging.
It's minus 1.67.
Okay. 1.
No.
No. Get rid of the 1.76 and change it to 1.67.
Okay.
And that gives you an answer of 1.08.
Okay, then you need to know E.
the voltage is trying to reach, whatever that is.
What they try to rate.
For that part is trying to reach 0
Perfect.
in the
That
start.
means if they keep going down, okay, that means they will be going down to 0. And the initial,
2.75.
okay, 2.75 minus 0. Okay, then you calculate, substitute into the formula. You can get the T low in here is 1, 1, 0 il second, microsecond. Okay, that's how to calculate the time for the signal at low.
Hey, Mr. Pham,
Yeah,
as far as T high, if T high is 86.2 microseconds and T low is 110 microseconds, what does that tell us about this circuit? As far as the time or frequency goes, what does this tell us?
now that's just telling you the signal look like coming out, they will be look like this one here. You see that?
Yeah,
That means that from here to here, that means the duty cycle. They're not 50-50,
okay,
okay?
okay.
So that is how do we calculate the time low. I just want to know, you get any question? If you're doing your calculation, then you're supposed to get 110 microseconds. I already get the calculation program for this thing. The thing I don't want to using my calculator to do calculated. I just enter the value so the computer will tell me. If it's not, then we go to the high. Okay, delta VC, T high means right here. Or here, the same thing. That's T high. Okay, so for T high, what delta VC equal?
It's the same, so it's 2.75 minus 1.67.
Yeah, same, exactly the same. Okay, that means they start from 1.67, they go to up to 75. So delta VC still be 1.08. Okay, A mean here, right?
Yep.
Difference between what?
So the final is 5
5 volt.
minus the initial of 1.67.
Perfect.
The 3.334.
Okay, 3.3.
3.33.
Okay, 3.33. Okay, if you substitute into the formula, you can get 86.2. Joule second. The thing is, if we given in the lab, I say I want the output to be 50-50. That means you have to select the resistor, capacitor in order to make the value. You have to using the value of R and C to calculate. You can get the same time for the high and for the low. Okay, and now after you get T high, T low, if they want to calculate the period, then you can see from here to here. That means the period will be T high plus T low. That you get the period. Okay, and if you want the frequency F equal 1 over T, that will be given you the frequency. And if you want the duty cycle, they will be equal to T high divide T high plus T low time 100%. On that calculation, you can get the answer will be frequency 5.10 kilohertz, and the duty cycle will be 43.9%. That is a completely calculation. Okay, for this type of circuitry. That means oscillator. Any question? I hope this time you can understand a little better. Okay, then we go into monostable. Basically, they can using the IC, okay, either 74121 or 74123. Okay, that means one they will be retrigger. Okay, the other one non-retrigger. First thing I can tell you, the output here basically depend on R and C. That means external connection. You can select R and C, so you can see the signal coming out will be how they will be look like. Okay, like they say right here, TW, the width. Okay, and this will be trigger. What that means? That means you apply the clock into the trigger input here, and the output they will be coming out. Okay. Basically, you get only one. However, if you keep applying like the square wave, clock signal coming in, then output will be coming out, keep going. Okay. And now, what that means when they say non-triggerable. Okay. And now you can see for your design, when they get trigger right here, and the output will be high, then here they will be going low. So even you get another pulse coming in, output they ignore. They don't care this one. Okay. Until the next one here. Then they can generate another one. That's what they call a non-triggerable or one shot action. Okay.
Mr. Pham,
Yeah.
can you pull down again? What is the difference in the waveform for A part and the B part? I see the same waveform for Q. Just only the difference is trigger.
What's the difference between on A and B, right?
Yeah, because the Q waveforms are almost same. I don't see any change in the Q output.
Right here.
Okay, so the difference is only for the trigger.
Yeah. However,
Okay.
they supposed to trigger, but they will not. They are the non-trigger, so that they ignore that guy until
Okay, got it.
Okay.
I got it. Thank
Now this is re-trigger. The same thing. You adding resistor and a capacitor externally. That's telling you how the point you want it. So normally you get a trigger here. Then the output coming out. Okay. Go to the next one. You get the output coming out. However, this is a re-trigger for this IC. When you trigger it, they can get another one. They supposed to be going down, TW. However, you get another trigger right here, and they keep going. Okay, that's what they call a re-trigger. So basically, the trigger coming in will be affecting into the output of the circuitry.
So where it is used, what is the use of this re-triggering?
Now, depending
What's
on
the basic use?
Yeah, basically depending on the circuitry, what they want, to design. When you get a trigger a little more than the output you wanted, okay? That's why they want the output get longer, okay? Instead, you can get only this thing here. Now they want it to be bigger, okay? So you have to apply another trigger, but that only working for 74123. Basically, if you really want to understand, then we can do the lab manually. Okay, that's easy to make a connection. And
Okay.
scope, oscilloscope to verify, then you can changing the R and C. You can see the pulse coming out, how long they will be. Okay. But that's just for basically you go to the college and they want to verify, make sure you understand it. They're doing the lab just using IC connect to resistor, capacitor, and they asking for what the output they want. Your job will be select the R, select the C in order to verify for the correction. But the thing is, we in this program only try to help you to fix the problem. Okay? So we don't care much about this thing. When you try to fix the problem in the company, engineering already telling you what they want.
Manage the fault.
Okay. Now, 555 timer. Also one shot. You understand one shot? That means what? The output coming out only one portion. Okay, high or low. And it.
You can use this one. Let me clear it. Use the other one.
Oh, this other one?
Yeah.
Okay.
Mute the mic, mute the
You have a
mic.
question, ma'am?
Just a minute.
Okay. What are you buying?
Okay, so that be a 555 timer. Also, they one shot. That means they just give an output one portion. Or they can be like unstable. That means they can get a signal coming out like oscillator. Okay. And now you can see this is the IC here. They get only 8 pins. Okay. Now see what's going on in the park in here. Inside that timer. So the first thing we have to understand what's going on each part in this one before you can understand how they working. Okay, if you get a VCC here, I say you get 15 volts. So that what voltage here?
15. Oh no, that's voltage divider.
Exactly.
Voltage divider.
Voltage divider. 15 times 5 plus 5 is 10. Divide 50. Divide to 50. So what you get?
Five volts.
You get 7.5 because both your resistors are the same value, so it's going to be half of the 15, right?
That's a voltage divider, right?
3 5.
15s cancel out, so it'll be 5.
You want the voltage at this point,
Yeah, I see.
so they will be 5.
5 volts.
Shouldn't it be 10? Shouldn't it be times 10 over 15?
Okay. What the voltage on this point?
That should be 5. The previous one should be 10.
So
I agree with that one. Previous one should be 10, not
okay,
5.
that's supposed to times 10, right?
Yes.
Sorry. Times 10. 550. So that's supposed to be 10 volts. And this is supposed to be
5 volt.
5 volt. Okay?
How much is the last resistor?
That means when you connect the voltage, the power, then pin 5, you supposed to get 10 volt. Pin number here will be going to this point here. Basically, and the outside you cannot get that. It's supposed to be 5. Now, this one, we're talking about this guy.
Which guy? This guy.
Comparator.
Comparator. They compare positive to the negative input. If a positive higher than the negative, output will be at the logical
High.
Okay, same thing happen on this guy. Positive connect to the negative. Okay, when the positive higher than negative, they will be high. Okay, if the negative higher than positive, they will be low. And this will be flip-flop at large. Okay, that means the output here, okay, they will be active low right here. You can see that. So if a 0 here, they go to the inverter, then they will be get 1. If you get a 1 input here, go to inverter, then get 0. Okay, now that one, this guy, the transistor, if you get a logic 1 here, okay, what happened to Q1?
Turns on.
Turn it on. Transistor will be on. When they on, they will be connecting 7 to the ground. See that? If you get a 0 here, the Q1 will be off. They not connect pin 7 to the ground. That is whatever happened inside the 555 timer.
Mr. Pham, can you explain the latch one more time?
Explain over.
The latch. Comparator A and comparator B.
Okay.
Output goes to the latch.
Okay. If input positive higher than input negative, then output logic 1. Okay. If input positive less than negative, then out. That's the logic. That applies for both. comparator.
So can comparator A and comparator B both simultaneously have 1?
No, I just try to explain to you in order to know what logic here, right? Then you have to know what pin 6 equal, what pin 5 equal. Then you can tell him what output supposed to be.
Yeah.
Same thing here. Okay.
Uh-huh.
Basically, you want to know the output, you have to know input positive and input negative. And that will be go into set or reset flip-flop. Then the output can be 1 or can be 0. Now, if I say output 0, that will be telling you turn Q1 off. If the Q1 off, only thing is they not connect pin 7 to the route. And if the output here at the logical 1, they turn the Q1 on. So they will be connect pin 7 to the route. That means you can see that pin will be discharged, charging, discharging. That means coming when you connect into the circuitry, they connect to capacitor. Capacitor charging or discharging. Okay? When they charging, capacitor Q1 must be off. When they discharge, Q1 will be on, so they connect to the route, they will be discharged. That's how they work. Okay, you can say 555 timer connect at a one shot. If you connect circuitry 555 timer this way, so you can able to get the output to be a one shot. Okay, and basically the TW, the width of the signal depend on R and C. Okay, the reason you get only one, that means they need to apply the trigger right here. One pulse trigger, you get one coming out. Only the difference is you can be designed for different TW. Maybe you want it bigger or you want it smaller, depend on R and C. Okay, and also they given you this formula here. Whoever want to play TW, that means the weight here. You can using formula 1.1 times R1 C1. Okay, this one we can do for simulation, not big deal. That means I say I want that the full weight to be how many microseconds or milliseconds, and you have to rejoin the value of R and C. Okay, and that will be in simulation.
Mr. Pham.
Yeah.
if you go back a couple of pages, back to the 74123,
Mhm.
right here, you got TW is equal to 0.7 RC. So what is the difference that give you different value of TW?
Okay. Basically, they talking about the weight in here. If you want the weight the way you want to design, you have to using this formula. Okay.
Can you say that again? I didn't quite catch that.
That means if you want the TW by how many, you know, microsecond, millisecond,
Mm-hmm.
then you using this formula, TW equal 0.7 times R times C.
Okay.
Okay. So I think we can get into the pitch part for the guy to design. That means I given the TW I wanted. And now you have to try to select R and C. You get the output we wanted.
So how can we know which formula we have to use for TW?
No, that's not working for 74123. If you open the data sheet for data IT, okay, and you can coming up with the width of the signal coming out, how you get it. That's not the formula.
Okay, so different IC will have different
Exactly.
TW, am I right?
Exactly.
Thank you.
Okay. Okay. Now I just go quickly to this one and we'll be stop it. First thing, you can see 555 timer at one shot. The pull width of the output is determined by the time constant of R1 and C1. Still the same formula here. Now try to see what happened. Okay, so they telling you, if you're looking here, this is the low. Okay, this is the low telling you pin number 5 will be higher than pin number 6, correct?
Mm-hmm.
Okay, so that's why this low. Okay, so this is low, and also on this one here, when they apply for the negative positive, okay, and this will be this this side will be higher than that one, so that's why you can get 1. Okay, you get 1 in here, so that will be set the flip-flop. Okay, set means they will be 1. Okay, they will be 1 and they go through inverter here. Output they will be low. Okay, so they 1, and when they go in 1 in here, okay, and they go to 0, this transistor will be off. That means they not connect pin 7 to the valve. Okay, and if you're looking into here, you can see the current. Okay, current flowing through R1. You see that? They going down, okay, to charging the capacitor. Okay, when the capacitor charging, that means the voltage at this point here, okay, will be changing. Okay, so they will be higher than a negative output now will be high. And that, okay, high, then that one supposed to be low. So they will be reset. Okay, that means the output will be 0. And when they 0 here, they turn the Q1 off. Okay, so Q1 off allow this one keep charging. Okay, what happened if you get a logic one here? So Q1 now on. When they on, they will be discharged. Okay, and that's why they keep going that way, charging and discharge.
Mr. Feb,
Yeah,
the comparator B output is 0. How the output is 0 for comparator B? I understand output is 1 for comparator A, but how output of B comparator becomes 0?
see here, right? Okay, when they
Yes.
when they 0, okay, that means, let's say, the negative have to be higher than the positive. Okay, and now normally what the positive wanted here?
It's 5 volt.
Okay, so it normally using 5 ohm here. Okay, then the voltage here will be what voltage? That
I
means
think so
5
around
times 5, right? Divide by 10. You see that?
1.67, is that right?
Whatever. Okay, 5 times 5 divide by 10.
You go 1 4.
Okay,
it's 2.5.
2.5.
2.5. Okay, so
Actually,
that means
by 15, Mr. Fan.
what?
Divide by 15, not by 10.
Yes, 15 divided by, 5 divided by 15.
Yeah, that's correct.
5 times,
ohm
No,
Right.
times 5K
right.
by
Divide
50.
divide by 15.
Yeah, sorry.
15
good.
So it's 1.67.
Yeah, and now it's correct. 1.6.
Okay, so basically when you apply the force here, so basically you can get 5 volt and 0. Okay, so when they get a 1.6 volt here, if you get a 0 here, that means this positive higher than negative. So the output will be high. Okay,
And so output will only remain high for the duration of the negative pulse at pin 2.
right. However, if this one go to low, 0, so now positive will be higher than negative. So that's telling you output here, they just like opposite to what you get here. Okay, so you can get the homework on the simulation. That will be helping you to understand more. Okay, when you try to simulate that thing. Now, I get the question why they call a one shot timer.
You only put one trigger in 2, the pin 2.
Exactly. You get only one applied, one negative pulse applied.
One pulse.
And the output will be only one positive coming out. No more. If you want more, you apply another one. Input negative positive. That's why they call one shot. However, you can see on that one, 555 timer are stable. You only need to understand stable. Stable means free running oscillator. Okay? That means the output, they will be go this one here. Keep going. Okay? And if you're looking in here, when you just turn it on, so the current will be flowing here. To charging R1, go to R1, R2, and charging for C1. So if you want to calculate the T high or T low, that means the formula T, right? Equal RC log 1 over 1 minus
C.
Okay, so when they charging here, what are? That is the charging.
So equal to R1 plus R2.
Exactly. R will be include R1, R2. So in this case, R in here equal R1 plus R2. Okay, now for the discharge, same formula. What R equal?
I believe it's only R2.
R2.
Just R2.
Exactly. Very good. The thing is, you see pin 7, turn on the transistor, right? They connect that to ground, right? If you look at pin 7, okay? Pin 7 right here. They will be connected to the transistor to the ground. So when they discharging, so the current will be flowing this way. They not go to R1. So discharging R will be equal R2 only. Okay? So now you can see they don't have any input applied to the timer. On this one, you get the input applied to pin number 2, negative positive. On this one, okay, basically pin number 2, they connecting to the output on the top of the capacitor. Okay, so that's why they keep generate the square wave coming out. And basically, T high or T low, depending on R1, R2, and C1. Okay, so in here they already given to you formula. If you want to calculate the F, it will be equal 1.44 divide R1 plus 2R2 times C1. You want the period T equal T high plus T low. T high equal 0.7 times R1 plus R2 times C1. T low, you only get 0.7 times R2 times C1 and a duty cycle, everything. Okay? So it will be done for today. Okay, again, make sure do either on take 1 or take 2. If you not take the AC fundamental, this time you better concentrate on that take 1. Okay? You don't have to be in take 2. Even your name still in take 2, that doesn't matter to me. Okay? Any more question? Anything else?
Hey, Mr. Pham, I need to share my screen with you.
Okay, so you want to share with me. I can stop that one. Okay. Okay, stop that. Okay, so now you want to share. That's okay to me. Go ahead and share. Whatever I can do.
Okay. Can you see that, Mr. Pham?
Yeah.
On line 273, what did I do wrong? This is D Lab 10, number 10.
273. Okay. You say void read memory, but you don't telling what your location you want to read. So like 270, basically you have to say read memory, okay, integer ADD.
What, right here?
Right.
Like INT A.
Okay, now in line 273, you write your memory address, they just ADD here, okay, they not integer.
Oh, okay. Yeah, okay, I got the circuit built. Let me see if I could.
But in your read memory, okay, decoration, you have to check that they have to get the same with the one you get in the function definition.
Okay, so I need to go.
You go up to get them read memory. I want to see decoration.
Yeah, right here, read memory.
Now where? Read memory.
No. That's the wrong location. I stopped you early.
You see that?
Yeah, so I got to put in
integer
INT
ADD.
space ADD. Okay. How come it got the red line in it? Oh, good, it went away. It might take a while. Okay, so now I go.
We don't using the test evaluation anymore.
Oh, you don't use this here?
Yeah, no.
Oh, so you like the, okay, so.
You can using read, port
So,
ASC. Yeah.
So you want to put this in?
Yeah, you have to put that in. If it's not, then you can using the different name. Instead using test evaluation, you can using test validate. That's
Oh, so,
okay.
you use test validate. Okay, wait a minute, hold on.
Yeah. The thing we don't want to using the same name with the name already inside the system.
Okay, wait a minute, hold on. So this is test.
Test validate.
Okay. VAL was I. Is that right?
Yeah, validate. IDE, right?
Validate.
DA,
ATE.
ATE.
E.
Get rid of the ION.
Yeah.
Then on so anything using the other one substitute by that.
Okay. So then, so now I got to go down the bottom. There's something where you can do like shift something and you can find them. I forget what it is. But in any case, I go back down. So right here.
I just copy and paste to be faster.
Yeah, you're right. You're right, Adam. So I'm just gonna do like this.
To me, Adam, he did very good. He
Yeah.
understand a lot.
Superstar.
Thank you very much.
Yeah, the thing is that when we try to teach your guy, okay, and I ask the guy question, when you answer it, I can tell him how much you understand. This is exactly the same what I did at the engineering in the company.
Get rid of that semicolon. There you
Yeah,
go.
that's what I was gonna do. That was my next move. So now, I don't know if I can do it where you guys can see, because I got the circuit built here. And I can run it. Build.
You have a couple more of the test validate to fix.
Yeah, I know.
You can
Yeah,
have that. You can have that in a bunch of spots.
yeah. I forget what it is. It's control something or shift something, and it takes you to where they're all at. Yeah, because I'm gonna have a bunch of errors.
Just click on that to see what error.
Pretty much at the end of every test.
Okay, so build, rebuild. Can you see the rebuild?
Mm-hmm.
You guys can see that? Can
Click,
you guys?
click on the first one. Click on that. They show you read memory. That is the wrong one, not the one we just telling you. How come you can get a lot of
I
things?
know you just because it was already in there, Mr. Pham, and you just helped me fix it.
You have to delete everything.
This here, right?
On the bar to the right, where all those little red dots are, those
Yeah.
are just the spots you got to go to.
Yeah. Mhm.
You want to read address. What address you want?
Okay, right. So that should be what, AA 0,
Depending on what you want.
like that.
Then that we have evaluation cap.
Yeah, the same thing. All right. So I'll
Okay, I can see the first one. You say you write memory address AA. You write data 55 and write to memory.
Whoop,
He dropped off the call.
I think we lost him. Okay.
Who done for that did lab? Adam, you done it?
Yes, sir. Mine is uploaded, and Mr. Pham said I passed.
Okay. He told me maybe two program. I don't know who else.
That'll be me, Michael.
Okay,
Yes, sir.
Michael.
Yeah.
That's an easy one. However, I'm working on the next lab still memory. But I given lab information. Then the guy try to see how many people can get through it. The first one, okay. The second one, more easier. And
After DLab 9, DLab 10 was easier.
right. Okay. So right now we be on 10, right?
Yes.
So the next one will be 11. That's what I'm working on. Just the memory. When you get along with how to deal with that memory, that will be more easier when you try to test a DDA converter. The thing I don't care is pass or fail. I really care, can you understand it or not? So when you run the test, if it's not working, it failed, then you have to tell me what you want to do. That is the way how to evaluation the student. Okay, Mr. Smith, just go home, okay? Okay, anyway, I will be end it now, okay?
Okay. Good night.
Yeah,
Thank
good
you,
night.
Mr. Pham.
We'll see you guys.
Goodbye, goodbye.
Mr. Pham,
Yeah,
I had a question. I was wondering if it's not too late still to get a permission to your class.
I wait already register for your guy. I believe so. You know, the one you sent it to Sam, right?
No, I don't I don't believe so. For summer tech 2.
You've been in the program from
Spring.
spring,
Yes.
spring 2021, right?
Right.
Okay, now what you can do, email to me with the,
Okay.
your ID number. I do it for you.
Okay. Okay. Sounds good.
Okay.
Perfect.
The thing
right,
is
thank you.
only next week, no more. We don't want anyone coming in. Only
Yes.
whoever want to drop, I can drop them.
Okay.
Okay. Just
Sounds good.
email to me.
Perfect. I will.
Yeah. Then tomorrow we'll be getting done.
Okay. Thank you.
Okay. Bye.
Bye.